today, our group will be presenting security vulnerabilities in automotive operating systems, remote exploitation of Tesla car's autopilot system. My name is Zainurisha and I will be starting off with a bit of background before passing it over to my crewmates. So let's start with something simple. Think about how much cars have changed over the years. In the past, a car was mostly just mechanical, an engine, some wheels, maybe a radio, but today cars are basically computers on wheels. They have sensors, cameras, and onboard computers that help with things like navigation, automatic braking, and even driving by themselves in certain conditions. Tesla is one of the companies that push this further. Their cars connect to the internet through Wi-Fi, Bluetooth, and cellular network. They can update the car's software remotely without the owner ever needing to visit a service center. But it also opens up a problem because these cars are not just handling your Spotify playlist, they are handling things like steering and braking. The benefits are pretty clear. Less driver fatigue on long trips, smoother reaction to sudden route situations, and continuous improvement through those over-the-air updates I mentioned earlier. But here's the thing, our report focuses on that same update system. The one that makes Tesla so convenient is also one of the most security critical part of the whole car, and that's exactly where things get interesting.
So now that we already understand what Tesla Autopilot is and why connected cars matter, now let's talk about the actual problem we're looking at. As vehicles become more connected, they also become more exposed. Every Wi-Fi connection, every Bluetooth pairing, every cellular link is basically a potential doorway into the car system. And if someone managed to catch you one of those doors, the consequences are not just about data or privacy. Although that's already serious, it can also affect the actual safety of the people inside the vehicle and even the people around it. This is what we mean by remote exploitation. In simple terms, it's when an attacker is able to interfere with or take control of parts of a vehicle system from a distance, without needing to physically touch the car. This could happen in a few different ways. Sometimes it's through the vehicle's own network connection, where an attacker exploits weak spots in how the car talks to its manufacturer's server. Sometimes it's through short-range wireless signals like Bluetooth or Wi-Fi, which can be tricked or intercepted. And also, sometimes it's through the cellular connection itself, where an attacker impersonates a network tower to sneak in. If you put all of these possible entry points together, you get what our report calls the attack surface. Basically, every possible point where someone could try to get in. For a car like a Tesla, this includes the long-range connections like cellular and GPS, short-range ones like Wi-Fi and key-fobs, the internal computer network of the car itself, and even the outside apps that connect to the vehicle. It's a surprisingly large surface area when you actually map it out. So, given all of this, what did our study actually set out to do? Our general objective was to look closely at the operating system behind Tesla's autopilot and connected vehicle platform, and to understand how real documented attacks have managed to compromise it in the past, and also what lesson that gave us. More specifically, we wanted to first describe how Tesla's different computing components are structured and connect that back to what we have learned in this course about operating system. Second, look at real publicly known incidents where Tesla vehicles were remotely attacked and figure out exactly what weakness allowed to each one to happen. 3. Evaluate how serious and how likely each of these threats actually is. 4. Look at how well Tesla's existing security measures have worked. And lastly, based on all of that, come up with some practical recommendations.
Let's start with how a Tesla is actually built. From a computing point of view, most car companies buy their infotainment screen, their internal network gateway, and their cellular connectivity unit from 3 completely different suppliers. Tesla does it differently. They design and build most of these components themselves, and combine them in a smaller number of custom, tightly connected computers. or ECUs. This lets them push out software updates faster, but it also means that if one part gets compromised, the damage can spread more easily to the rest of the car. There are 4 components you really need to know: the central information display, the instrument cluster, the autopilot processing engine, and also the gateway ECU. Now, let's talk about what happens when this goes wrong. And we look at 5 documented cases. The first, and honestly the most dramatic, happened in 2016. Researchers from Kin Security Lab found that Tesla cars automatically connected to a known Wi-Fi name used at service center. So, they simply broadcast a fake network with that same name. From there, they escalated all the way to the gateway ECU and were able to remotely control the brakes, the door locks, and even the sunroof from 19 kilometers away. Later incidents shifted focus. In 2018 and 2019, the same research team showed that placing a few small stickers on the road could trick autopilot's camera into thinking there was a lane there and there wasn't one, steering the car towards incoming traffic. Around the same time, researchers found weakness in the key fob system, allowing attackers to clone key in just a couple of seconds using cheap radio equipment. Then, in 2022, a 19-year-old researcher named David Colombo found that he could remotely control a 25 Tesla vehicles. Interestingly, the flaw wasn't in the Tesla-owned system. It was in a third-party app called Tesla Meet, where some users had accidentally left their access token exposed online. And more recently, from 2023 onward, professional hacking competitions have continued to find new vulnerabilities in Tesla's gateway, infotainment, and cellular systems every single year, even though Tesla keeps patching and hardening its defense. Every single one of these incidents also connect back to the core operating system principle. Things like least privilege, code signing, memory isolation, and redundancy. I let my next groupmate take it from here to talk about what we found and what we actually recommend.
Thanks, Hilmi. So, let's bring this all together. Looking at these 5 incidents across almost a decade, we can see a clear pattern. The earliest and most severe attack in 2016 exploited basic fundamental weakness, things like unintercepted password and no proper code verification. Tesla fixed that fast, and no similar attack of that scale has happened since. That's a good sign. But the attacker didn't just give up. They moved to a softer target. They added off the system like the key fob, third-party app, and the cellular modem. Instead of Tesla-owned hardware core, the 2022 Tesla Meet incident made this thing really clear. Tesla-owned system was fine. The problem was a third-party app that user connected to it, and that teaches us something important. A system is only as strong as its weakest connected component, no matter how secure the main system is. We also noticed something interesting when comparing feasibility and impact. The easiest attack to actually carry out, like key cloning, caused moderate damage. But the attack that could cause the most damage, actually, control over steering or braking, needed serious expertise or physical access to the road. That's not an accident. That's what a layered security design is supposed to do. Based on all of this, we came up with 6 practical recommendations. First, Tesla and similar platforms should tighten how third-party apps access vehicle data, using short-lived, limited access token instead of broad, long-lasting one. Second, keep running structured, ongoing security like PWN 20WN instead of treating it as once-a-year event. Third, consider using more specialist safety certificate operating system for the most critical component instead of general-purpose software. Fourth, upgrade keyless entry system industry-wide since the same weakness keeps showing up across different manufacturers. Fifth, apply stricter, safer core practice for anything connected to the network. And sixth, simply make sure debug port and hidden access point are disabled before a car ever leaves the factory. So, to conclude, this case study showed that automated cybersecurity really is just operating system security, applied to something with much higher state than a laptop or a phone. Tesla has clearly matured a lot since 2016. From a system that could be tricked with simple checksum to one with cryptographic signing and redundant cross-checking hardware. But the But the fact that professional research keep finding new way in year after year tell us that no connected vehicle can be called completely secure. It's an ongoing process, not a one-time fix. For us, working on this case study really drove home something we haven't been learning throughout this course. That concept like a process isolation, memory protection, and access control aren't just exam topic. They are an actual engineering decision that keep people safe on the road. That concludes our presentation. Thank you so much for listening and be happy to take any question.